Hey everyone, welcome back to the YouTube channel, An American Professor. We're going to continue where we left with the basics and introduction to reinforcement learning series. Last time I had a co-host, a guest narrator, my best friend Zane Price, and in that video we gave a gentle introduction to reinforcement learning. This time I'll continue on in that series and we'll learn more about what is state in reinforcement learning. The simple answer, it is what the engineer says it is. That's what state. But we'll get into more of the weeds and the technicalities of this. So let's continue our read along and continue learning about the amazing subfield of AI, reinforcement learning. A state in reinforcement learning is a representation of the current environment that the agent is in. The state can be observed by the agent, and it includes all relevant information about the environment that the agent needs to know in order to make a decision. The state can be represented as a vector of values, continuous or discrete, or even be a set of Boolean values. That is it this or something else, 1 or 0? You can encode information using Booleans. In addition, the state can be stored in the agent's memory and recalled at any time during the learning process. For more general, practically speaking, most of the time we just model the states as being Markov, which means we only need to know the current state for the agent to act optimally. If a system, however, is non-Markov, then that's where memory becomes more important for decisions leading to the best rewards obtained into the future. The state is an important part of reinforcement learning as it allows the agent to keep track of its progress and make decisions based on previous experience. In reinforcement learning, state is defined as the set of information that an agent has about the environment at a given time. This information can include the agent's current position, the objects around it, and any previous controls that it has taken. The state of an agent also includes its memory, which stores information about past states, also referred to as history. The state is important because it allows the agent to plan its next controls based on its current situation and its goals. Without state, an agent would have no way of knowing what it has done in the past or what it needs to do in the future. Next, let's ask, what is state space in reinforcement? So we talked about what are states. State space is the set of all possible states. So in reinforcement learning, the state space is the set of all possible states that an agent could be in. This includes both the current state and all future states that could be reached from the current state. The state space also defines the set of all possible controls that an agent can take and the set of all possible rewards that an agent can receive. It is important to note that the state space is not necessarily finite. That is, it could be some compact disk and we could have an infinite number of states in that compact disk. But usually for Markov or MDP-based formulations, we have a discrete set of states, usually discrete and finite. It can also be infinite depending upon the model used. For example, if an agent is learning to play a game, the state space would consist of all the possible game states that could be reached from the current state. If the game has an infinite number of possible states, countably infinite, not real, like the real line infinite, but countably infinite, then the state space would also be infinite, countably infinite. For a specific example, in a game of chess, the state space would include all of the possible configurations of pieces on the board. In order to choose the best control at each step, the agent needs to be able to keep track of all the possible states and identify which state it is currently in. The state space can be very large and complex, particularly in games with a large number of possible states, although still finite. However, reinforcement learning algorithms are designed to efficiently explore and learn from state spaces in order to find optimal policies. So let's run through some examples of state and reinforcement learning problems. In reinforcement learning, the state of an environment is defined by the current observable values of that environment. For example, and we'll continue the series I've started in reinforcement learning on tic-tac-toe soon in an upcoming video, but now I'll talk more about the conceptualization of that problem or that task that needs to be solved by a tic-tac playing RL agent. In a simple game like tic-tac-toe, the state would be defined by the position of the X's and O's on the board. I have started a tutorial series on this game already. To start learning more about applying reinforcement learning for this game, you can read these 2 articles that I've already written on the topic. In a more complex game like chess, the state would be defined by the position of all the pieces on the board. In a real-world application like controlling a robot arm, the state would be defined by the position and velocity of the arm. The examples given here are just a few of the many possible states that could be used or defined in reinforcement learning problems. The important thing to remember is that the state must be fully observable to the agent so that it can learn from this experience of the states it's encountering and make decisions accordingly and reliably. There are many other examples of reinforcement learning problems outside of board games as well. Board games or games in general is just one class of possible applications of reinforcement learning. And those are all competitive, by the way, not cooperative with other agents. You're competing against some other player or agent. For instance, in business, companies often use reinforcement learning algorithms in order to optimize their advertising campaigns or stock portfolios. In medicine, reinforcement learning has been used to develop models that can predict how well a patient will respond to different treatments. And in robotics, reinforcement learning is often used to teach robots how to complete tasks such as moving objects from one place to another. Just think of one robot that is moving some part and maybe in an assembly line from one place to another. Reinforcement learning has been successfully applied to a wide variety of examples, ranging from gaming applications to industrial control. Some more examples of states and reinforcement learning problems include 1, robots moving through an environment. This could even get into the multi-agent modeling realm where you have a swarm of robots moving into space. Or 2, automated collection of data. 3, automated stock trading. 4, energy management in buildings. And 5, anticipation of human driver error in self-driving vehicles. In each of these examples, the agent is trying to learn how to optimally interact with its environment in order to achieve a goal. This can be a difficult task as the agent often does not have complete information, it only has partial information usually, about the environment or the long-term consequences of its controls. However, by carefully modeling the problem and using trial and error, the agent can learn how to best achieve its goals. So let's go through some examples to make state-based reinforcement learning more concrete. So let's give some examples of those. In computer science, a state-based algorithm is one that uses the current state of a system to determine the next control. For example, consider a very simple state machine with 2 states, A and B. If the machine is in state A, it will transition to state B when it receives control X. If it is in state B, it will transition to state A when it receives control Y. This type of algorithm is often used in finite state machines, abbreviated FSMs, which are commonly used in computer systems to track and manage system states. In an FSM, each possible state is represented by a unique code, and the transition from one state to another is determined by a set of rules. State-based algorithms can be used to solve many different kinds of problems, from simple puzzles to complex network routing problems. In general, they are well suited for any problem that can be represented as a series of states and transitions. There are many ways to use states and algorithms. One common example is using a state variable to keep track of the current position in a list or array. This is often used in search algorithms, where the state variable is used to store the index of the element being searched for. Another common use of state variables is in memoization, where they are used to keep track of previously computed values. This can be used to speed up algorithms by avoiding repeated computations. Finally, State variables can be used to implement randomized algorithms, where they are used to store the current seed value. By using state variables in this way, algorithms can be made more efficient and easier to understand. As another example, consider a simple alarm clock. The current state of the system, that is the time, is used to determine when the alarm should go off. Similarly, a state-based routing algorithm would use the current state of the network, that is the congestion levels on each link, to determine which route should be used for each packet. State-based algorithms are often used in real-time systems where the controls must be taken as soon as the state changes. This is because state-based algorithms can react very quickly to changes in the system state. However, state-based algorithms can also be used in non-real-time systems, such as stock trading or web browsing. In these cases, the reaction time is less critical and data from past states can be used to make better decisions about future states. When we only need the current state to make optimal control decisions, we call the system Markov, as I've said previously. Most systems are inherently non-Markovian in the real world. Some final thoughts on state and reinforcement learning. In reinforcement learning, the agent is faced with a complex task and must learn how to complete it through trial and error or solve this given task. This can be an effective way to train an agent, but it can also lead to some issues. One potential problem is that the agent may become too focused on the task at hand and neglect other important tasks, assuming it has multiple tasks that need to be solved. Most often, we model one RL agent as solving one task. This is particularly troublesome if there are multiple tasks that an agent should be completing. Think of sub-goals to solving a larger important goal. But one way you could potentially come around this issue is have train each agent for each of those sub-goals, rather than having one agent assigned to all the sub-goals. Additionally, the agent may not be able to learn from its mistakes if the task is too complex. Finally, reinforcement learning can be very time-consuming and may not always converge on a solution. Despite these potential drawbacks, reinforcement learning remains a popular approach in artificial intelligence research. Other issues with state and reinforcement learning are: how do we best deal with many questions such as how to use past states to determine the present or future state of the system? That is, it can be hard to predict based on a given policy how certain future states are reached, maybe given a very stochastic system or with lots of random disturbances, or even partially observed state. How, how can we also ensure that the agent does not become trapped in a local optimum? This hits at the issue of convergence issues, such as it may not always be possible to approach a global minimum to your objective function for the task at hand. Also, tracking state can be difficult, especially in large or highly complex systems. In addition, using state can be computationally expensive, which can limit the number of trials or episodes an agent can run in a given period of time. As a result, reinforcement learning algorithms that use state often need to trade off between accuracy and computational efficiency. This is usually referred to as the curse of dimensionality. In general, the state can be very complex and difficult to work with in reinforcement learning. While it can provide helpful information about the environment to a decision-making agent, it can also lead to issues such as partial observability, as I've discussed somewhat. Reinforcement learning problems can be broadly classified into two types in terms of the state, characterizing the problem based on the state or the agent, that is fully observable or partially observable. Although there are other possible characterizations to RL problems, to name a few, you could have a multi-agent RL problem, or it could just be the classical single agent problem, one task for one agent. With a fully observable state, the agent has complete information about the environment. This makes learning considerably easier. This means that the agent knows the state of all relevant variables at each stage of decision making. However, in a partially observable state system, the agent only has access to a limited set of variables. As a result, the agent must use its observations to infer the underlying state of the environment. Many real-world problems are only partially observable, making them challenging for current reinforcement learning agents or algorithms. Some examples of these problems include robotics, natural language processing, and financial modeling. In each of these domains, the agent must learn to extract useful information from partial observations in order to make good control decisions. Until next time, if you're curious to read on more of these articles, you can visit my Medium page here. That's all for this video. I'll see you next time.